Okay. Hello, my name is Ethan Silver. I'm a rising senior at the University of California, Berkeley, and a current intern at SLAC. And along with Elena Orlando of the University of Trieste and Stanford University, our work is in comparing propagation models with local cosmic ray spectra. First, I'll start with introducing the Galprop code, developed at Stanford and the Max Planck Institute over decades to simulate cosmic ray propagation through the galaxy. Galprop is our key tool for simulating local interstellar spectra for each cosmic ray species by numerically solving the cosmic ray transport equation. And the transport equation shown here includes terms that govern cosmic ray sources, diffusion, convection, reacceleration, energy loss, spallation, and decay. Then our two most important sources of cosmic ray data are Voyager 1 and AMSO2. Voyager 1, of course, is the probe launched in 1977 and now outside the solar system. It primarily provides data on low energy cosmic rays, especially from around 0.1 to 550 MeV per nucleon. And its data is unaffected by solar modulation experienced within the solar system. Meanwhile, the AMSO2 detector has provided data on higher energy cosmic rays since its installation on the International Space Station in 2011, especially above 1 GeV per nucleon. And AMSO2 provides us with data that's of an unprecedented high precision that basically allows for much stronger constraints on cosmic ray propagation models than was previously possible. So one of the primary goals of this work is to revise different cosmic ray propagation scenarios. And here we consider 6. Firstly, we have 3 DRC models, which include diffusion, reacceleration, and convection. DRC1 has 1 break in the spectral index of each species. DRC2 has 2 breaks in the spectral indices. DRC-conv is a variant of DRC2 that also has 2 breaks in the spectral indices, but with a much stronger convection term with dVdz greater than 50 kilometers per second per kiloparsec. Next, we revise a DRE model, which just has diffusion and reacceleration, a PD model, which is plain diffusion, and a DC model as well, which just includes diffusion and convection. In order to fit the propagation parameters for each model, we use the Minuet2 software to find the best fit parameter values, where we compare the model spectra against the data in each of the cosmic ray species. In the fitting, we in particular focus on the boron to carbon ratio. So basically, because boron isn't produced as a primary cosmic ray species, and it's instead mostly produced through collisions and interactions of other cosmic rays, especially carbon and to a lesser extent oxygen, with the interstellar matter. So the result of this is that B over C can strongly constrain many of the parameters of different cosmic ray propagation scenarios, especially regarding diffusion. So our best fit models generally have a diffusion coefficient ranging from 2.7 to 4.6 times 10 to the 28th centimeters squared per second using an isotropic diffusion coefficient. And each model uses 1 break in the diffusion coefficient at fixed at 370 GeV, with delta 1 around 0.4 below the break and delta 2 around 0.2 above it. And depending on the propagation scenario, the best fit Alfvén velocity can range from 0 to around 52 kilometers per second, while for convection, dVdz can range from 0 to 55 kilometers per second per kiloparsec. We also include a factor of beta, or V over C, to the power of the free parameter eta, which ranges from 0 to 1. And this addition can improve model performance at low energies. So to examine the best fit models, we can look at the boron to carbon ratio first, where here we are comparing the unmodulated spectrum shown in the solid black line against AMSO2 data and ACE-CRISS data. And we are comparing the unmodulated spectrum against Voyager 1 data and the modulated gray spectrum against AMSO2 and ACE-CRIS data. So firstly, here we are comparing DRC1 and DRC2, which have quite a similar overall performance. And of course, DRC2 has an extra break in the spectral indices, which leads to a slight improvement in the model's agreement with the data at the peak of B over C, and to some extent at low energies as well as compared to Voyager 1 data, at the cost of the larger parameter space that the extra break incurs. Then looking at DRC-Con, it also has a good agreement in B over C, but when all the cosmic ray species are included, it does end up performing worse than DRC2. DRC-Conv has dVdz fit to 54 kilometers per second per kiloparsec compared to values of around 12 kilometers per second per kiloparsec for DRC1 and DRC2. It also has the alpha velocity above 50 kilometers per second versus just under 30 kilometers per second for DRC2. DRE is another model that can match AMSO2 B over C data quite well, although it is higher than most of the Voyager 1 data points. DRE does perform a little worse than both of the DRC models, so the inclusion of convection does end up helping the cosmic ray propagation models. Next, the PD model with no reacceleration or convection terms performs a little worse than DRE in turn. The PD model can still match most of the AMSO2 data well, although it provides a lower energy peak of B over C of around 300 MeV per nucleon than other models, which have it closer to 1 GeV per nucleon. However, PD does still fall within the error bars for all of the AMSO2 data points, which is an unexpectedly good performance for a PD model that doesn't include a low energy diffusion break. Finally, DC ends up being similar to PD, but strictly worse for the majority of species, making it the worst performing model overall, even though it is an extra parameter adding convection as compared to PD. For instance, for B over C, DC is similar to PD, also having the same low energy peak, but it does have a worse agreement with Voyager 1 data. Next, we can explore the behavior of the different models for each of the cosmic ray species. Here we have starting with hydrogen, helium, boron, and carbon. And so here we're starting with the best performing model, DRC2, where the model falls within the reported error for nearly every AMSO2 and Voyager 1 data point. And generally, all of the models agree with most of the data well, and the differences between the models come in specific imperfections in certain parts of the spectra. And so we can compare the performance of this best performing model, DRC2, with the worst performing model, DC. And so here it still agrees with most of the data for each of the species, but there are some clear flaws. For example, in the helium spectrum, the unmodulated spectrum is below some of the Voyager 1 data points, and the modulated spectrum is above some of the AMSO2 data points in the range of around 500 MeV per nucleon. And for carbon, it can also be seen that the model is slightly too high at the highest energy levels. Then considering some of the more massive species of oxygen, neon, magnesium, and silicon, again, looking at DRC2, we can see that DRC2 also agrees quite well with the data for these species. And again, we can compare how this performance looks to the performance of the DC model, which has several apparent issues, most notably an overproduction of oxygen when compared to much of the AMSO2 data. And this problem also manifests in a lot of the other models to varying degrees because oxygen affects the boron to carbon ratio, and a decrease in the model spectrum of oxygen would essentially lead to a lower boron to carbon ratio as well. In addition, DC slightly overproduces magnesium, and just generally, if you look at all of the species, it just has a bit worse agreement at both high and low energies.
2 minutes.
So one useful way to analyze the different models is looking at the diffusion coefficient's dependence on rigidity. As displayed in this model, in this figure from Strong et al. 2007, plane diffusion models, shown with the dashed line, generally require a break in the diffusion coefficient at low energies, leading it to turn upward below 1 GeV, whereas models with reacceleration shown with the gray line do not. So for the diffusion coefficient for each of our 6 models, each one has one break at 370 GeV. And so our PD model does not turn upwards at low energies as a result, although it does decrease slower than the other models due to the eta parameter being fit to near 0, making the diffusion coefficient nearly a simple power law. And this plot shows some of the other differences between the models, such as that DRC1 and 2 are quite similar at higher energies, but diverge somewhat when you go to lower energies. The major purpose of our work is to present these revisions of various cosmic ray propagation scenarios using the latest cosmic ray measurements. And so overall, DRC models with 2 breaks in the spectral indices perform the best, having the most degrees of freedom. And we explore the effects of the other scenarios as well. DRC1 with only 1 break in the spectral indices is the second best performing and is only slightly worse than DRC2. And leaving out convection reacceleration as seen in DRE and PD models does hurt model performance somewhat as well. We demonstrate that PD models exist with no need for a low energy diffusion break where the diffusion coefficient turns upwards. And we show that DC models and DRC models with strong convection with VDZ greater than 50 kilometers per second are both disfavored by cosmic ray data. Thank you for listening.